Ready to start whenever you are.
Yeah, I'm also ready. So, hi guys, we'll be starting the workshop now. So, how many of you attended the last week's workshop? Almost all of you. Okay. So, okay, whoever didn't attend, it was more of an introductory session. So we didn't cover any like technical topic as such. We just went over a few basic pre-processing techniques. So you would no need to worry about it. Today we'll be going over a few things. So let's start then. So today we'll be going over text representations. Like how do you represent text so that the machines can understand it, right? Like humans can understand the language as such, but machines we need to do some processing to so that to in order to make them understand it. So so as I said, last week we went over the text pre-processing steps, and uh, due to lack of time we couldn't go over bag of words model, so we'll be covering that part as well. And today we'll be covering n-grams and tf-idf techniques. And so let's get started. So bag of words model. So so bag of words model, it's a very easy and simple technique to represent text words in numerical form. So what you basically do is you have a corpus. Corpus means data set in here NLP. So we use the word corpus. So corpus is a list of let's say sentences. Let's say this is AI society. This is a sentence. So what you do is you will have multiple sentences like this in multiple documents, right? So you will create a vocabulary out of all the unique words. So for example, let's take two sentences. This is AI society. So how many unique words are there? This is AI society, 4 words, right? So vocabulary size here is 4. And based on the frequency of the words, if the word is present in a particular document, we will assign 1, or if it is not there, we'll assign it 0. So let's see example. So this is example, right? The NLP is fun and I love NLP. So the vocabulary here is all the unique words in the document, and the representation is as simple as we'll just say if the word is present in the document 1 or not. Similarly for document 2 or not. So similarly, if we have multiple documents and multiple such sentences, will form a matrix of this kind, so that we can do then some kind of processing that we need to do, and use it in any application. So this is one of the earliest and easiest way to represent words or text in a numerical form. So and as you can see, the advantages are it is very very easy and like simple to implement, easy to understand as well, and it works well with smaller data sets on small like simple end-to-end tasks. But there are many limitations in it. So can you think? Okay, here I have written it, but can you think of any limitation? Like what can be the drawbacks of this? Does it consider the context or the order in which the words are coming? No, right? Like, and is it also considering the polysemy, or the same word can have multiple meanings? For example, the word bright. Bright can means a bright student, or in this like with respect to color, it's bright. So it can have same word can have multiple meanings. So it doesn't capture that. Other thing is yeah, so it is sensitive to the presence of stop words and noisy data set. So stop words, one solution as we discussed in the previous workshop is that we can remove the stop words completely. But in some applications we might need stop words. So there it will, it is very sensitive to that, because then if the number of stop words are more, the table that we are making like this 110. So if stop, so in every sentence there is a stop word, like NLP is fun. So is here a stop word. I love NLP. So I can be a stop word. So like this, the frequency of is will be too much here. Let's say it comes 100 times here, and rest of the words are coming 5 or 6 times. So it will be very skewed. So you don't want that. And as I said, does not handle synonyms as well. like same like multiple words having same meanings, it is not able to capture that. So basically there are many problems with bag of words, though it is very very easy and simple to understand, but it has many problems, and there are many. So we'll look at a better way to represent words. So these are some of the applications, like text classification. You can, so let's say you want to uh, make a application for spam detection. So let's say you have multiple documents containing text or emails. So you want to classify it as spam or not spam. So how can you do that? Using bag of words. So what you can do is, like, generally in spam emails, you will have some kind of words ki join, like click this link, or uh, yeah, $1 million, or some like catchy phrases. So those phrases, you can make a bag of words matrix, and then if the certain words are present, based on that, you can classify it as spam or not spam. So it's a very like easy application. You can build it on your own also, just as exercise. Again, sentiment analysis, same concept, same kind of intuition ki if the like NLP is fun. So if there are, you can have a vocabulary like that, and you can then store a list of words like fun, loving, or something like that. And if certain words are present, that means it's a positive sentiment. You can have a list of negative words like bad or depressing, like that. And if certain words are present in the matrix, that means that sentence is negative sentiment. So like that, you can use bag of words in certain applications, but overall, like the the point where NLP is today, bag of words nobody uses right now. Like GPT, we have language models right now, which will be covering in this lecture, a part of it. So so bag of words was a very 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 traditional method, which at a point, like in these kind of applications, to certain extent it worked, but it is not a very very good text representation method. So so another similar kind of method is term frequency inverse document frequency. So it's a very, so it is, there are two words in this, term frequency and inverse document frequency. So what does term frequency mean? So it means how often a term appears in a document. Okay, so it's a simple term frequency. You count the number of times a word is appearing in a document. That is term frequency. And similarly, there can be multiple documents. Let's say there are 10 documents. So term frequency is only specific to a particular document. In document one, a word, let's say NLP, is coming 10 times. So that is term frequency for that document and that term. So as you see, term frequency has two arguments, term and the document. So term, for that term in that document, what is the frequency of that term? And inverse document frequency. So what it does is, it weights the term based on its rarity. So one of the drawbacks of the bag of words model was, it was very very sensitive to the stop words, right? If stop words is like too large, the number of stop words, then it won't perform well. It will give more weightage to those stop words. So to counter that, like TF-IDF has a good advantage over it in that respect, because it has this inverse document frequency. What it measures is how rare a word is across all the documents. That's why if you see, inverse document frequency is only dependent on the term, not on the document. So it sees all the documents in the corpus, and how rare the word is. It is dependent on that. We'll see the formula for that in some time. So what it does is, it helps prioritize important unique words in documents while downplaying common terms. And common terms are generally stop words, which we don't want. So this is one of the major advantages of TF-IDF over bag of words model. So this is term frequency. So as I said, term frequency depends on two things: term in that document. So it is the frequency of a word D in document D divided by total number of words in D. So that is a term frequency. So let's say this is we have a corpus of two documents, A and B. And in document A, we have one sentence: Jupiter is the largest planet. in document B, we have this sentence. So now we need to find term frequency for document A and document B, because as I said, term frequency is dependent on term as well as document. So for term frequency A, so first of all, the first step will be to create a vocabulary for all the words across all the documents. So we will take Jupiter is the largest planet, Mars is already there. So this is the vocabulary, and then we'll try to calculate the term frequency. So the term frequency formula is frequency divided by the total number of words in that document. So for document A, Jupiter comes one time, and the total number of words in document A is 5. So it will be 1 divided by 5. Similarly, for term frequency for Jupiter in document B, how many times is Jupiter coming in document B? 0. So 0 divided by 5, 0 divided by 8, 0. Similarly, we can calculate term frequencies for all the words in all the documents. Here we have 2 documents, but if you can have like as many documents as you want, and you can calculate the term frequency. And then you move ahead. We'll move ahead to inverse document frequency. So inverse document frequency, as I said, is inversely proportional to the number of documents containing T. So what it gives is how rare a word is. So for example, let's say, let's consider the stop words, right? So the frequency of stop words will be higher, let's say 100. So if you put here number of documents containing T, so it will come in all the documents. Let's say we have 20 documents. So 20 plus 1. And if a word is coming in only one document, so the denominator will be less, right? So only 2. So it is inversely proportional to the how rare a word is. So if a word is rare, the value will be higher. If the word is very common, the value of inverse document frequency will be lower. So, and one more thing, we are adding 1 because some words in the test set can be out of vocabulary which we have not seen before in the training data set. So then the denominator will convert to 0. We don't want that. That's why in those cases we can add 1 to the denominator. So let's see example. We have the same corpus. So, and we calculated the term frequency. Now let's look at the inverse document frequency. And log here is the natural log. So total number of documents, we have 2 documents. So numerator will be same for all the terms. So divided by number of documents. So here, since we don't have it, we are only considering the training vocabulary words, we don't need to add 1 here. So 2 divided by how many times Jupiter, in how many documents Jupiter is present, only 1. So we calculate the value of inverse document frequency. As you see, is a stop word. It is coming in both the documents. It is very common word. That's why inverse document frequency for that is 0. So now the total thing, as you saw in the first slide, TF IDF value is the multiplication of term frequency and IDF. So term frequency. So tell me one question: why don't we only consider the term frequency, and why do we need inverse document frequency? What will happen if we don't consider the IDF? It will skew the data, right? Yeah, again, as I said, it will be similar to then the bag of words model. The stop words will take, more like it will make it skewed, because that's why we need IDF here. And that's why we are multiplying it by that. And the final output will be the multiplication of both these terms. Again, the advantages are, as I said before, it weighs based on the importance. The importance means how rare a word is. And it discount the common words. And limitations, again, the same limitations. It doesn't see the context. By context, I mean it doesn't differentiate between synonyms, or it doesn't the ordering of the words, like the order of the words, it doesn't consider, and cannot handle complex relationships. So again, the example of the word bright, it will not capture if the word has multiple meanings in the same document. Okay, so these are many limitations in TF-IDF. So before we move ahead to n-grams, because it will take time, let's go over the code of bag of words and TF-IDF quickly. So you can take out your laptops and work.
The code base and the PPT is sent on the Discord channel. So if you can just open
Yeah,
the drive link,
yours.
you'll be able to access it.
So yeah, we are going to look into the basic steps that is required to build a bag of words, and we'll be cleaning the data set and doing the basic steps. So basically, uh, so in the bag of words, first we'll be tokenizing the text. So in this example, we have a zip file, so which has a couple of files, around 10 files something. So each file has some specific data. In this case, we have some data about some organizations. If you guys can look into the Discord channel, so we'll be extracting those files and we'll be reading every single file inside the zip and then tokenizing them, every single word, and then we'll be converting them to the lowercase, and then we'll be removing the stop words, which is and those things, and we'll be stemming the words, and then we'll be lemmatizing the words, and finally we'll be building the vocabularies and building the vectors so we can visualize the results. So I'll go one by one. So first we'll be tokenizing the text. Yeah. So we'll be passing the text to this tokenized text function. So it will use a split function to return it as an array. I mean, every single word will be an element in an array. So that's how it tokenizes. Then we'll be changing the tokens into lowercase so we can handle it efficiently. So we cannot just handle it if it's like capitalized somewhere and in middle of some word. So we just make it to lowercase. Yeah. Here we are just using a for loop and just lowercase and returning the values. So then we'll be removing the stop words. Remove stop words. Yeah. So in this example, we just took some stop words, the and is in at often and. So we are using this function to remove the words. We are just using, if it's not the stop word, we are just returning the tokens and then we are returning it in the remove stop words. So now we are stemmonizing the tokens, which is removing the suffix of the common words, common suffixes from the words. Sorry. So as you can see, these are the common suffixes we have in with some words: the ing, lyd, ious, ies, and ie. So we don't need these suffixes to make our tokens complex. So we are just removing these things. So here we are just using a for loop and removing the tokens, removing the suffixes. Now we are lemmatizing the tokens. Usually, lemmatization I don't think everyone does, but we have an example for that. So basically, as Rajat explained before, we have a lot of vocabularies for single meaning: better, good, and run, running, run. So for the sake of making the tokens simpler, not complex, so we'll be replacing the words. So in place of better, we'll be having good. In place of ran, we'll be having running, run. So this kind of things we'll be doing with the lemmatization. So finally, we'll be building the vocabularies according to the bag of words with this function. So yeah. So yeah, here we are just counting the number of occurrence in the each array, each tokens. So we'll be which we are just using an for loop to count the array, count the tokens, and then we are just returning the things. So now we have the count of each vocabulary, and yeah, yeah. Now in this vectorized text, sorry. So yeah. Now, according to the index, whatever the tokens we recorded here, we are counting the each tokens count in the vector text vectors. So these two functions are the major functions. This builds the array of vocabularies that we have unique vocabularies in the data set, and this records the occurrences of those vocabularies and the vocabularies. So if you see the output, you can see three things. In file 1, we have these tokens, and these are the vectors. I mean, the newspaper that occurred is 1984 times, and then the cycrypt is that occurrence is 2070. So the total vocabulary count is 32,208. You can map. I mean, you can map the indexes from tokens to vector. So this happens to each files. I limited here because it has a lot of words. It will take a lot of time to process, so I just limited it to 10. So do you guys have any doubts here in the code or somewhere? Okay. We have shared a template as well. If you want, you can use that to practice too.
Okay, let me open. So I'm Toshal, and now we will look at the TF-IDF code, and I will also explain the n-grams one after the theory is done. So here I have taken the movie review data set, and it is like usually used for sentiment analysis, but here we are not taking the sentiments into account. So we will just look at the data set. So first of all, I have downloaded it directly. And this is the structure of the data set, how it is. So these are the folders in the data set, and then there is in the test folder, you can see there is of like two folders that are important to us, which is like negative folder, positive folders. They are probably for the sentiment, which we don't really need. So we are just gonna take one of the folders because we need to just work on some data set for this TF-IDF. So so first of all, we are just gonna see what the data set looks like. So these are the reviews in the data set. As you can see, like people have given reviews. These are the top 10 lines in the data set. What we are gonna do is we're gonna make put this reviews into each rows in a data frame. Data frame is basically a table. So we're gonna do it. Okay, so in this code, I was like actually putting the sentiments as well with the data frame, but since it's not required, we don't have to do it. So we have like created a data frame called train data, in that we have put the reviews in each rows and the sentiments associated with it, and like we don't need to require the sentiment column. So this is how the data set, like data frame, looks like, and you use .head command to show the like data frame. It shows the top 5 rows of the data frame, and if you want to see more rows, you can just add the number in the bracket. Then this is just like looking at the unique values which are there for the sentiments. So now we need to pre-process the data frame. So as you can see in this data frame, in each rows, the reviews are something that some things in it are not that important for us to give. Like it won't help in calculating TF-IDF values. So we're gonna pre-process it. And I'm not going to do it from scratch. Like I use the NLTK library to directly pre-process it. So as Prabhakaran already told you about all of this, I'm just going to skip. So after pre-processing, it looks like this. So this is the process text. So as you can see, the although in the A on it is like capital and here it's small, and then it has removed the stop words as well. So we are gonna use the process text. Now so Rajat already told about the theory for TF-IDF, so I will just go into code. This is like a small code. It's just directly we can do the TF-IDF directly from the sklearn library, but I'm gonna tell the like how it's calculated manually. So TF is like how many times a term appears in the documents. So in this, we are like counting the number of terms in the document from the scratch. So we are using we are just counting it. And then we are like trying to find a portion or maybe probability of like the word divided by total number of words. And that's what this function is doing to calculate TF. And then the IDF is it tells about how rare a word is. So if a word is rare, then it will have a greater IDF value. And if it's not rare, if it's like frequent, it will have lower IDF value. So we are calculating it by directly applying the formula that you saw in the PPT, which is log of total documents divided by 1 plus the like documents which have that word. Then to calculate TF-IDF, we are just gonna multiply the TF values and IDF values, and that's what this like code does. It just multiplies it. It's a function for that. Now we're gonna see. So this is like I'm calling those functions, and like now for the term frequency, this is what the output looks like when we try to run the code. So as you see here, the rows are the documents. So 0th row is the first document, and although is some word in it divided by total number of words that document. So that's what these values are. And then for the inverse IDF, the value is like for Amazon, the value is 2.7 something. So maybe it's rare. And if we see for Matter, the value is lower. Maybe it's more frequent than Amazon. So that's how you look at the IDF values. And we just multiply it and calculate the TF-IDF values. And yeah, that's how you like calculate TF-IDF values. Yeah, right.
Yeah, we'll start the n-grams now. So, first of all, n-grams is an ambiguous word in NLP. It is used also for text representation, and n-grams is also a language model. So, first we'll just cover quickly the text representation part, and then I'll give you an intro of what language model is and what n-gram language model is in particular. So, let's go over the n-gram, which is used for text representation. So it is very similar to just the term frequency part in TF-IDF, but instead of one word, we take a sequence of words. So for example, n here represent the sequence of words. So if n is 1, that means we are taking just one word and calculating its frequency. For example, let's say machine learning models is a sentence. So if it is a unigram model, unigram means n is equals to 1. We'll just take one word, machine, and count the frequency of that word. Similarly, if it is a bigram model, n is equals to 2, we take two sequences of words, machine learning, like two words at a time. And the second word in this bigram model will be learning models. And if it is a trigram, we'll take three sequence of three words at a time and calculate the frequency of this machine learning models, how frequent this whole sequence is instead of just a word. So again, what advantage it gives over TF-IDF and bag of words is it captures local semantic meaning. So what it means is it takes the order of the words in account, which TF-IDF and bag of words was not doing. But again, the disadvantage is if a word comes which was not in the training vocabulary, it will suffer. One more thing is, though it captures the local semantic, it doesn't take into account the long-term dependencies into account. So we'll see that. But it overcomes some of the limitations of both TF-IDF and bag of words. But but still, in some of the latest architectures, none of these techniques are used for text representation. These all are some of the whatever text representation techniques we saw are very traditional representation techniques. In current scenario, most the byte pair encoding, which I shared in the last lecture, those kind of tokenization methods are used, and we'll see in subsequent lectures what the current architectures use when we'll study those particular architectures. So these were the three which are popular text representation techniques, although they are not used now. So as I said, n-grams in NLP is an ambiguous word. It also represents a way of text representation, but it is also a language model. So before understanding what n-gram language model is, let's understand what a language model is. So any model that computes the probability of a sentence. So W1, W2, W3 are the words in the sentence. So let's say we have n words in a sentence. Let's take the sentence NLP is fun. So it has three words. So it will capture the probability of those sequence of words. So this is the main idea of what the language model should do. But again, we can rephrase the same thing in another way. That what is the given we have four words, what is the probability of fifth word given all these four words? So let's say we have in the sentence NLP is fun. We have two words, NLP is, and then we want to predict what is the next word that will come based on these two words. So any model that either computes the probability of sequence of words, or if it calculates the probability of an upcoming word, that model is called a language model. So whatever you are seeing now, the large language models, this is the key idea. So what ChatGPT does is, it will have a sequence of words. So here in n-gram, the n is very, very small. But in because, as I said, it has a long term, I'll talk about it. But ChatGPT, what it does is it has, let's say, 1,000 words. It will predict the next word. So this is the core idea of any language model, be it small or large. Okay, so as the definition goes, models that assign a probability to each possible next word. That is called a language model. So this is the idea of language model. Let's now see. So as you saw here, we want to calculate the probability of a sentence or sequence of words, right? But how do we calculate this probability? So how do we calculate the probability of that sequence of words W? So for that, we'll use like chain rule of probability. So for example, if this is the sentence, how to calculate the probability of this sequence of words. So we'll use chain rule of probability. So uh, uh, do you guys know what a conditional probability is? I'm sure you must have studied it, even if you might not remember it. So I'll just go over the formula quickly. This is the chain rule of probability. This is different than conditional probability, but this comes from conditional probability. So let's say we have just two words, okay? Probability of A given a word B. The formula for that is probability of A and B divided divided by probability of A. So if you if you just want the probability, so this comma this in this way means probability of W1 and W2 that dash dash till Wn. So this comma means and. Okay, so in that formula for conditional probability, if you transfer the denominator to the other side, you will get probability of A given B into probability of A for this part. So similarly, I said this formula for two terms, the conditional probability formula for two terms. If you expand it to n terms, this is what you will get. So if let's say we have four terms, probability NLP or three words, NLP is fun. So probability of NLP into probability of is given NLP, like second word given the first word, into probability of fun given the first two words. So this is, so you can expand it to n number of words. So like the probability of the nth word given the first n minus one words. So this is the chain rule, and you multiply it. Yeah.
Could you write it on the board? Like what
We have the
NLP is
board.
on?
Oh, yeah, yes. Yeah, so probability of A given B. So that is, so A is a, let's say here is a word, and B is a word which comes before the word A. So probability of A and B. So this term can be written as same as probability of A comma B. So comma generally represents and divided by probability of A. So here, B. So here we want this, right? A sequence of words, like we want A, B, C, D. It can be till like Z, Z or N words, right? So we want this probability. So we need to transfer this here. So we'll get, let's say, if I change the notation to W1, what we have is W1 and W2. So it will be probability of W1 into this will go and this probability of W2 given the first word. So this is for two terms. So let's say the two words are my name. Okay. So probability of, so this is the, let's say this is the whole sentence. My name is one sentence. So this is W. So we want to calculate probability of my the sequence of words in the sentence name. So this will be equal to probability of my first name, because this is the first character, into probability of name given the all the previous tokens before name. So here we only have one my, like this. So this is for 2 words. We can expand this for n words. So probability of w1 till to n is equals to probability of w1 into probability of w2 given w1 into probability of w3 given w1 and w2, and then similarly till probability of wn given w1 till wn minus 1. So same thing is written. So this is a multiplication, right? So this is a symbol of multiplication. N is equals to 1 till n. Sorry, I is equals to 1 till n. So probability of wi given w1 till wi minus 1. So this is the chain rule of probability. It comes from this formula. So same thing is written here. And so yeah, so as I said, for this example, we have the first probability of the first word into probability of second word given the first word, and so on. So this is how we'll calculate the probability of this. But there is a problem with this. We'll see that. So now, as I said, we'll compute it like this. Let's say, how do we calculate probability? Is this count of the whole word divided by the which is in the given part, the evidence part. But let's say we have a huge corpus. Okay, or let's take the case of ChatGPT or a big large language model. It was trained on all the web data that is there on the web, right? So it's not possible to count the have the counts of these sentences, correct count of these sentences. So then what do we do now? We can't just count and take the division of it. There are too many possible sentences and will not get it correctly. So the solution for that is we use something known as Markov assumption. So what Markov assumption, and Markov assumption you will find it in like many fields, like in reinforcement learning and different fields. So n-grams, the intuition of n-grams is based on Markov assumption. So the what Markov assumption is that you can find the approximate the probability of a word is dependent on its recent history. Okay, so given a word, it is only dependent on its recent history, not its whole history. So what it means is, let's say we were calculating the probabilities, right? Keep probability of wn given w1 till wn minus 1 from like its whole history. But what it says is you can just take the last like 2-3 words, like the recent before it, and calculate its probability, and it will be approximately equal to the its actual probability. So, and that is the intuition of n-grams. So what n here represents is how much history to take into account. So for example, initially we saw the formula for this was we are taking the like in the evidence part, we are taking given w1 till wi minus 1, right? But for unigram model or by so if there is an n-gram model, in the evidence part you will only have n minus 1 terms. So again, I think I'll use the yeah. So for example, here as we were seeing, yeah. So let's say we have a so let's say we have a sentence NLP is fun, or a longer sentence, something I am And so like this, we have a long sentence. So now probability of word. So we have a n-gram model. N is equals to, let's say, 3. So let's consider probability of soccer. So probability of soccer given will take the last n minus 1 words. N minus 1 is 2 here. So last 2 words. M and 2 words. If it was 2, we'll take just 2 minus 1 last word. We would have taken just the last word. So initially what we were doing was we were taking the whole history into account. Now we will take based on this n. If n is whatever the n is, we will take the last n minus 1 words before the current word. So and it will be approximately equal to its like actual probability if we consider the whole history. So that is what Markov assumption is, and on this idea, the n-gram language model is based upon. So yeah, so as you see, this is an example. You can switch. Yeah, so as you see, so unigram means n is equals to 1. So 1 minus 1, there is no evidence. We'll just calculate the probability of without any evidence. If n is equals to 2 bigram model, you will consider only last word, like probability of wi given the last word before the current word. So this is what the n-gram model is. So it solves many of the problems. So if you see here, there are some issues with n-gram language models. One is, as I said, it is not a sufficient language model. So for example, the current large language models are not based on n-gram model. The reason being, it doesn't incorporate the long distance dependencies, right? So for what I mean by that is, let's consider this sentence. The computer which I had just put into the machine room on the 5th floor is crashing. So this crashing is related to the word which had come in the beginning of the sentence. So the sentence, this is even a small sentence. Or let's say you have a paragraph, and the last line of the paragraph is referring to the first line of that paragraph. So it is a long-term dependency, right? So n-grams can't handle this long dependency. They are good at handling like a local context. Like if it is within n is equals to 5-6 words, they will be able to handle it. But long-term dependencies, they can't handle it. So this is a big problem. So I think in next lecture we'll learn about advanced language models like transformers and everything, which which solves this problem by using something known as attention. So, but if we just ignore this problem of long distance dependency, this n-grams model still work well. Like with n is equals to 3 and 4, you will get a good sentence. So as I said, it captures local context, and it is a very simple and intuitive way to as an introduction to language model. And it is computationally efficient. So whenever I say computationally efficient, it is always relative to something. So it is computationally efficient relative to the current language models, right? So like large like chat gpt or anything, it is very, very like 100 or 1000 times efficient than like n-grams is 1000 times computationally efficient than those models. And so one more thing. So in practical scenarios, whenever we use n-grams, we generally we consider the log space. What I mean by that is, you saw that we are multiplying probabilities. So what we do is we change into log of that probability. The reason is that to avoid underflow. So probabilities, if you when I think the code will be presented, you will see the values will be very, very, very small, like 0.001. If you multiply this value by another small value, the resultant value will be even small. Okay, to remove this problem, we convert it to log, so that the computation becomes easier, and also we don't. So if you consider, if you take the log of a into b, it is log a plus log b. It changes to addition. Okay, so it is faster than multiplication. So in any real case scenario, wherever n-grams model is used, we convert the probabilities to log of p instead of just p. And yeah, as I said, as n increases, we need to have large amount of data as the n will increase, because again, as you saw, we are taking a sequence of words in consideration to to solve to predict the next word. So as n increases, let's say n is equals to 5 or n is equals to 6 or n is equals to 20, so it needs to have so let's say the sequence that will form after if n is equals to 20, that sequence should be more frequent. Otherwise, its count will be 1 and the prediction values will be very, very small and it won't be very efficient. So, to have, as n will increase, we need to have a lot of training data to compensate that. And also, as I said, it doesn't capture the meaning or relationships beyond a certain words. And all, yeah, so before this, so I think I haven't included one slide, which is how do we compute if this, you know, this whatever the sentence that is formed is good or not. We use something known as perplexity, like which is a like we have accuracies in simple machine learning. So for to see if the sentence formed or the next word predicted is correct or not, we use something known as perplexity. So perplexity is nothing but just the inverse of this, like the sequence of probability of the sequence of words and the nth root of that. So lower the perplexity, the better the sentences. And like a few more cases may arise. So again, like how do we handle out of vocabulary cases, right? Like if you see, like when we are taking the probability, we are taking the count of words. So what if the sequence of word in test set that is coming is not in the vocabulary? What do we do in that case? So we use something known as smoothing techniques, which so there are one famous smoothing technique is Laplace smoothing technique. So what we did in the inverse document frequency case, right? We added a one in the denominator. The same thing is Laplace smoothing. You add a one so that the division, the denominator, you will never get a zero. So so in and also in real world, a few so what you generally do is you never use just a bigram model or a trigram model. What you use is a combination of all the models. So let's say you are developing a n-gram model for a certain application. So what you do is, it is known as interpolations. What you do is you generate a 1 gram model, you'll generate a 2 gram model, you'll generate like this till let's say 5 gram model. After this, what you will do is you will take certain weights of all the n grams, lambda 1 into 1 gram plus lambda 2 into 2 gram dash dash is lambda 5 into 5 gram model. So and whatever will be the resultant model, you will use that as the final model. So and that is seen to give better results than just using a single n-gram model. So like these are some of the tricks that are used whenever n-gram models are used in real life scenarios in certain applications. Um, and so you can read about, like there are many small things like these, like back off, or these back off technique, in which you keep on like going backwards. Like let's say you start with n is equals to 5 gram, but you see that the training data is not enough for n is equals to 5 gram, so you'll go back to n is equals to 4 grams and see that if the model whatever is predicting a good value or not, like forming good sentences or not. If not, you'll go back to n is equals to 3. So that is back off technique. So if you like want to learn a few, like I think I've covered almost all the important things here. But if you want to read more in detail, I think about these small techniques, you can. There is a Stanford course by Professor Jurafsky. He has a book. He had a book written on this Ngram models and NLP in general. So you can the Ngram. You can read the Ngram language model part in that. So yeah, I'll hand it over to Toshil for the core presentation for this.
I think we're towards the end of the
Okay.
lecture. So we'll do the coding for the Ngram model next week. But before you go, we have a small questionnaire prepared. So what happens is this is like a leaderboard. Every week towards the end of the workshop, we'll have a set of questions, and the people who like towards the end of the semester, we'll have we'll be this is a cumulative test, and towards the end, the top winner, prize winners, top winners will be awarded with some prizes. So make sure to log in using your ASU ID, give in your correct credentials, because this is going to be recurring every week. Yeah. Please go ahead and.
Yeah, and one more thing for this week's test, we have also included questions from the last week because we were not able to have a test in the last workshop. So in this, you will also find some basic pre-processing techniques based questions.
Everyone who is not given your attendance, please make sure to come here and give your attendance in this. Also, we had a small announcement about the lab openings for Coral Lab. They mostly work on multimodal LLMs, focusing on semi-structured data with charts and tables and stuff. So if you're interested, if you have relevant experience, please make sure to fill the Google form. And yeah, so if you have any questions, please